Hello guys, so in this video I'm going to talk about how to use the second derivative test to test for concavity, and typically use the second derivative test when you're doing optimization. So without further ado, so the first step we need to do is we need to find the first derivative of this function. And we can simply do this by taking the derivative of f of x. So the derivative of f of x would be negative 5x to the fourth minus 27x squared. And then the derivative of a constant is simply 0. So now we have f prime of x. The next step would be to take the second derivative. So we're going to differentiate one more time because this is the second derivative test. The derivative of this function would be negative 20x cubed minus 54x. So this is the second derivative. So now what we're going to do is, the key step is we are going to set f double prime of x, so the second derivative, we're going to set this function equal to 0. Then we will solve x. So the first thing we're doing is we're setting 0 is equal to f prime of x, which is equal to negative 20x cubed minus 54x. So we're going to go ahead and set this equal to 0. So in doing so, 0 is equal to negative 20x cubed minus 54x. So whenever we have the set equal to 0, we can actually just go ahead and set these equal to each other. So we're going to move the 20 over the other side of the equal sign. So we're going to change the sign. So it's going to be 20x cubed is equal to negative 54x. And now we're basically just solving for x. So x, oh yeah, this is 54x. So the first thing we can do is we can eliminate an x on each side. So this would be 20x squared is equal to negative 54. And how did I do that? Since they both have an x, I divided both sides by x. And in doing so, the x over here cancels and the x over here is now x squared. So now we're simply just going to we're going to solve for x. So x squared is equal to negative 27 over 10. All I did was simplify the 54 and the 20. And now in order to do this, we have to take the square root of both sides, which means x is equal to negative square root of 27 over 10. And since our x comes out to be less than 0, we have a function that is a max. So since, just looking at these conditions up here, since our x is equal to a number that is less than 0, or equal to a number, a number that is less than 0, we have a max. So whenever we have a max, we have a concave down. So the graph having a max just basically means that you have a graph that looks like this, that's going concave down. That's what the second derivative test does. We're testing for max and min. And since x was a negative number, we have a max, which means concave down. And that's how you apply the second derivative test. Step 1, take first derivative, differentiate. Step 2, take the second derivative, differentiate again. Step 3, set f double prime of x equal to 0, and then solve for x. When you solve for x, if you have a negative number, it's a max. If you have a positive number, it's a min. All right, guys, that's all I have for y'all. Thank y'all for watching. I hope this was helpful. Hello, guys. So in this video, in this example, we're going to go over how to apply the second derivative test. And typically we do this for optimization to see if we have a max or a min. We can do the second derivative to test our work. So like, for example, if an optimization problem asks you, what's the minimum area that this yard can be or whatever, then using the second derivative test, you should get a min. If you get a max, then that means that you either messed up on the second derivative test or in your optimization. So without further ado, the first thing we do is we're going to find f prime of x. And we do that simply by taking the derivative of the function f of x. So f prime of x is equal to 4x cubed minus 2x. And then the derivative of 4 is 0, so we're not going to include it. And then step 2 would be to find the second derivative, f prime of x. So in doing that, f prime of x is equal to 12x squared minus 2. And once we have the second derivative, the key step would be to we're going to set f double prime of x equal to 0. So f prime of x is equal to 0, which is equal to 12x squared minus 2. And all we're simply doing now is once we set it equal to 0, we are going to solve for x. So we're solving for x. So right here, what we can do is we can actually, since 0 is equal to 12x squared minus 2, we can actually just set these equal to each other since we have a 0. So we're going to move the 2 over here. We're going to add 2 to both sides. So 2 is equal to 12x squared. And then the next step would be to simplify this. So we're going to divide both sides by 2. And in doing this, we get 1 is equal to 6x squared. And then the next step is, in solving for x, we're dividing 1 over 6 is equal to x squared. And then the final step would be to simply just take the square root of both sides. And in doing that, the square and the radical cancel each other out. So we are left with x is equal to 1 over 6 inside a square root, and the square root of 1 is 1. So if you want to simplify it a step further, you don't have to. You can leave it like this, and then you could go on and radicalize it if you want to, but again, you don't have to. So I think you can leave it like this. You should get full credit. So x is equal to the square root of 1/6. So what does this mean? Do we have a max or do we have a min? Well, since this is a positive number, since f double prime of x is greater than 0, we actually have a min. We have a minimum function. So basically what this means is that the graph looks something like this, where it's concave up, because you have a minimum point. So it means that the graph must be going up. So we have what's called a local min. So that's what the second derivative test does. It measures to see if you have a local max or a local min. So in this case, we have a local min. And the graph is when we're testing for concavity, it would be concave up. All right. Thank you guys for watching. I hope that was helpful.